Well, welcome back to Math 221. Um, we've got a couple of different things to cover today. So let's jump right into the first topic, which is going to basically be putting to use what we looked at in last Thursday's lecture, this past Tuesday's lecture, and sort of putting that all together and using it to sketch curves. Okay, I'm going to give us two examples. And then you'll have a handful more in your homework where you can kind of, practice basically putting together and utilizing all of the information. We're going to do one polynomial and then one rational function. Okay, so let's take a look at our first one. Let's say we're going to graph, yes, since we're graphing, y, which is a function of x, which is x cubed minus 6x squared plus 9x plus 2. Okay, and there's sort of a number of steps that we want to go through. Okay, the first one is we want to look at the domain. Okay, and I'll number these for us. And we want to look at the domain so that we know like what we should be trying to graph, right? And since we're a polynomial, our domain is the whole real number line. Okay. 2, we want to take a look at the x and y intercepts. The y-intercept is going to be fairly easy, right? The y-intercept happens when x equals 0. So all of these terms are 0, right? And we're left with 2, okay? So the y-intercept is 2. Now, in the case of the x-intercept, in order for us to solve for the x-intercept, right, we would need to solve the equation x squared, or x cubed minus 6x squared, plus 9x plus 2 equals 0. And this guy doesn't actually factor very nicely. Occasionally, you'll find these that do, and you could go through your rational roots theorem to test this. But since this doesn't factor, at least doesn't factor nicely for us, we're not going to worry about the x-intercept, and we'll keep going through our steps. Okay. Step 3, we'll want to take a look at the limits at infinity. So as x goes to infinity, of f of x, well, this is a cubic function with a positive leading term, right? And that's going to tell us that its end behavior is going to do this. So the limit as x goes to infinity is going to be infinity, and the limit as x goes to negative infinity is negative infinity. Okay, so we know that. Next, we would normally want to take a look at asymptotes, whether they're vertical or horizontal. Obviously, if they were horizontal, they would have showed up here, right? But since this is a polynomial, there are none. Okay. What about step 5? For step 5, we can take a look at where the function is increasing and decreasing. And to find that, we can take a look at the derivative. So it looks like the derivative is going to be 3x squared minus 12x plus 9. Okay? All of that has a common factor of 3. It's going to be x squared minus 4x plus 3, and that's going to factor nice and simply into x minus 1, x minus 3, okay? And then we can grab one of our little sign diagrams and take a look at where we'll need 1 and 3, and we can pick a handful of points, right? If we plug 0 into this, we're going to get 9, so all of this is positive. A 0 there and a 0 there. What happens if we pick something in the middle, right? If I were you and like I were doing this, it might be best to write these calculations down, but I'm right at the bottom of the page, so why don't we just talk through them instead, right? So if we're going to pick 2, 2 minus 1 is 1, and then 2 minus 3 is actually minus 1, so we get 3 times 1 times minus 1, or a negative 3 for being negative there. And then what's happening somewhere like here, right? Like maybe we can pick 4, right? X minus 1, that's going to give us 3. X minus 3 is going to give us 1. So we have 3 times 1, or 9, which is positive, right? So since we know this about the first derivative, right, we know that my function is increasing here, decreasing there, and then increasing again there, right, on these intervals. And then I'm actually going to copy this and put it onto our next page, just to keep track of this. Because 6, we want to look at a local extrema. Okay, and we can see from this, right, at x equals 1, we're going from increasing to decreasing, which means this is a local max. And then here at 3, we have a local min, right, because we're going from decreasing to increasing, right? That's the first derivative test. And then we should actually, figure out what these values are, right? So if we were to go f of 1, going back to our function, that's going to be 1 cubed, or 1, minus 6 times 1, plus 9 times 1, plus 2, which is going to come out to, it looks like, a total of 6. And then f of 3, what's going to be 3 cubed, minus 6 times 3 cubed, plus 9 times 3 plus 2, and if you run through all of that, it comes out to 2. Okay, so that's going to give us our value on the local extrema. Step 7, we can look for concavity, right? And we're going to need to look at our second derivative for that. When we take our derivative one more time, we're taking the derivative of this guy. So it looks like this 2 is going to drop down, and we're going to get 6x minus 12, or 6 times x minus 2. Okay, so this is going to have a 0 at x equals 2. And then we can build our second derivative test here. We have a 0 at x equals 2. If we pick something bigger, right, say 3, 3 minus 1 is 1. Sorry, 3 minus 2 is 1, times 6 is positive. And then we can pick, something like 0 over here. And then from that, we can easily see that we're negative all there, okay? So that tells me that we're going to be concave down here, concave up there, and that, I guess you could consider this step 8 is inflection, if I could spell it right, inflection, and that's going to happen here. Then we can evaluate f of 2, and when you run through f of 2, you're going to get 4, okay? And then now that we have all of this information, we can put it all together, much like this, right? And then actually use it to put together a graph, okay? So maybe we'll do this. And we'll have we will go double here, so that's 2, 3, 4, 5, and then 1, 2, 3, 4, 5, 6. Okay, and we want to slowly start building our information in. And the best place to start is actually to grab some of the points that we know. So we know that we have a y-intercept at 0, 2. So we'll do this in purple. We know that we have a local max at 1, 6. We can just do that to sort of remind us of its behavior. We know we have a relative minimum at 3, 2, something like that. And we know we have a point of inflection at 2, 4. Okay. Well, what else do we know? We know that we're increasing. We know that we're increasing here. We know that we're decreasing here. We know that we're increasing here. And we know we're concave down here and concave up here. Okay. And if we combine that with the information from last lecture, right, where we sort of looked at the interplay between, increasing and concave up, increasing concave down, and all of that, then we can fill in the rest of our information and know that our graph is going to look something like this. Something like that. Okay, it's not a perfect sketch. Doing these sorts of graphs on an iPad like this is actually a little bit harder than you would think. It's much easier on a traditional chalkboard. And let's go on to our next one. Let's say again, y equals f of x is x plus 1 over x minus 1, right? One of the ones that we sort of looked at earlier in these, series on curve sketching. So we'll go through the same sorts of steps, okay? Our domain, there's a number of different ways to write this. I'll just write it like that. So it's everything except for 1, okay? And then 2, let's look at my intercepts. Okay. If x equals 0, well, then it looks like y equals -1, right? And then let's set y equal to 0. If y equals 0, then x plus 1 must equal 0. So then x is equal to -1. Okay. 3, we want to look at its end behavior, right? As we sort of talked about right at the end of last lecture, we already know that the limit as x goes to infinity of f of x equals the limit as x goes to -infinity of f of x, and that just equals 1, right? There's a horizontal asymptote as x equals 1. For step 4, vertical and horizontal asymptotes. Once again, we discussed this previously. There's a vertical asymptote at x equals 1, and then there's a horizontal asymptote at y equals 1, as we saw here. Okay? What about step 5? Well, step 5 was asking us to look at our derivative. Okay? And so we need to take a derivative. When we take a derivative, we have to use the quotient rule here. So we're going to get low, d high, but the derivative of the top is just 1, minus high, d low, but the derivative of low is just 1, over low, low. And then if you'll notice here, it looks like we have x minus 1 minus x minus 1. So my two x's cancel. Then we're left with minus 2 over x minus 1 squared. Taking a look at our sine diagram here, we're not going to have any zeros of this derivative, but we are going to have one place where it's not defined, and that's at 1. Right? Our function does not exist there. And so we can pick a series of test points. If we were to say pick 0, we have negative 1 squared, which is positive 1. And so we're negative here. And then if we pick something, I don't know, say 2, 2 minus 1 is 1, 1 squared is 1, and then so we're negative once again. So what's interesting is that our function is actually always decreasing. Right? We're decreasing here, and we're decreasing here, and importantly, there's not a relative extrema here. And further than that, right, we know that our function is not going to have any local extrema. Right? There's only one place where the derivative could give us a critical point, x equals 1, but notice that's not even in our domain. So f has no critical numbers in the first place for us to even consider, okay? If you recall, part 7 was looking at the second derivative test. And then if we were to take a look at the second derivative test, we'll need the second derivative test, which you can get from the power rule. I'll let you confirm that yourself. This is going to be our second derivative. We're going to have a similar looking second derivative test, right? Our point of interest, right, is once again at 1, and our function does not exist there. Pick a couple of test points. Let's say start with x equals 2. 2 minus 1 is 1. Cube it stays positive. A positive divided by a positive is a positive. And then what's happening here? Well, we can pick, say, 0. Then we have minus 1 cubed, which is minus 1. And then we see we're negative there. Okay, so that means that we're concave down here and concave up there. And then step 8, points of inflection. Once again, none. The only, quote candidate would be x equals 1, but as we've already said, that's not in our domain. Okay, and rather than rewriting that, I'm just going to start graphing and reference the pieces as we need it. Our domain is going to be everything except x equals 1. There's going to be a little hole right there. And that makes sense, right? Because we remember we have a vertical asymptote at x equals 1, which I'll label. Okay. And then we also have a horizontal asymptote at y equals 1. Handy to know. And what else? We know that our intercepts, are going to be negative 1, 0, and 0, negative 1. So negative 1, 0, and 0, negative 1. Okay. We know that this asymptote here, we sort of did this, we did this last lecture, but we know that our one-sided limit from the right is going this way, and our left-handed limit is going down. What else do we know? Well, we know we're always decreasing, right? We're always, doing something like this, right? We also know that we're concave down um, on the left side of this interval. So that's going to point us to doing something like this. And then we're concave up on the right side. That's going to point us to doing something like that, right? And you could absolutely go through, pick a like handful more points, either on this side or on this side to, get a more accurate sketch of the graph. Um, but that's sort of how we can build on the tools that you would have used and learned in a like pre-cal class for graphing these. We can build on those with these ideas that were handed by the first and the second derivative to sort of up the game when it comes to sketching curves.